We've known that machine learning can be used for many wonderful tasks, such as speech recognition, spam detection, machine translation, and so on. Today, I'm going to introduce another one, how to use machine learning to fix a wrecked voice. People could gradually lose their voice due to some diseases, such as Parkinson's. In the early stage, the symptoms mainly reduce the speaking rate. With the progression of the disease, patients could completely lose the ability to communicate using their speech. As the patient's speech becomes harder to be understood, they may start to use some communication aid. These devices normally consist of a keyboard and a text-to-speech system, which generates speech according to input texts. Text-to-speech, or TTS, is a typical use of machine learning. It is a system that takes text as input and outputs speech. To build such a system, we need to train two neural network models, a duration model and an acoustic model. The duration model controls the speaking rate of the synthesized speech, while the acoustic model outputs acoustic features that can be used to create the final audio. As for training data, we need some test speech recording pairs. Before training, there is a pre-processing stage that prepares training data to a suitable form. In this stage, input texts are first converted to a sequence of phones. Together with provided speech recordings, the duration of each phone can be calculated. This gives us numerous phone duration pairs, which can be used to train the duration model. We also pass the speech recordings through something called a vocoder, which extracts acoustic features from the phones. Now we have some phone acoustic feature pairs. These can be used to train the acoustic model. The next step is training the two neural network models. The principle behind how machine learning works is actually simple. A neural network model normally consists of an input layer, an output layer, and some hidden layers in between. When we have more than one hidden layer, we call it a deep neural network, or DNN. The aim of all DNN models is the same. For given inputs, give correct outputs. During the model training process, we provide the input and target output. Initially, the model generates some output that is very different from the target output. It then calculates the difference or errors, and the neurons will learn to minimize these errors. When the errors go down to an acceptable range, we say the model has finished training. In our case, for given phones, a trained duration model will output duration information, and the trained acoustic model can output acoustic features. With the trained duration and acoustic models, text-to-speech now becomes very simple. For given texts, we convert them into sequences of phones. Corresponding DNN models will then predict the duration and acoustic features of these phones, which can then be fed into a vocoder to create the final speech. Now we know how the system works, but how much data do we need to train such DNN models? The answer is a lot. For this example, to generate natural speech, I used 100 hours of recordings with text transcriptions. If we want the synthesized speech to sound like the patient's own voice, can we just get 100 hours of recordings from the patient? The answer is very unpractical. First of all, it is rather hard for the patient to speak now, not to mention about making 100 hours of recordings. Second, the recordings cannot just be random conversations. They need to follow a specially designed script to make sure it covers all phones extensively. Lastly, even if the patient can make recordings following the special script, remember they have disordered speech. If the training data is disordered, the final synthesized speech will still be disordered. Then how can we do this? Here comes speaker adaptation. The idea of speaker adaptation is adapting a TTS model to a target speaker so that the synthesized speech sounds like the target speaker. The beauty of this is that it requires very limited data from the target speaker. To be exact, just 6 to 7 minutes of recordings in our example. We can use 100 hours of healthy speech recordings from numerous voice donors to create a healthy baseline TTS model. Then, we use 6 minutes of patient recordings to make the adaptation. During adaptation, the patient recordings add weights to the neurons in the baseline acoustic model so that they generate acoustic features which are similar to the patient's speech. In this way, we complete the task of restoring a disordered voice to its healthy version with a very small amount of data. Let's listen to an example of a disordered speech.
It's extremely important for me that young people get a taste of really good work.
And an example of the fixed speech.
It's extremely important for me that young people get a taste of really good work.
That's our content for today. Thank you for watching and I hope you enjoy this video. See you next time.